Hey, welcome to our video demonstration of our Characterizing Elements experiment. I'm Joe. I'll be explaining the background of the experiment, and then we'll start showing you the types of data that you should be collecting. You'll all be getting report sheets. The report sheets you would normally fill out. We'll send those to you by PDF with some data that we've scribbled in there for you, and you'll be able to complete your labs. Okay, in this experiment you use spectroscopes. Here's a spectroscope. You'll be using spectroscopes to observe line spectra from discharge tubes. These are discharge tubes. This is a tube filled with mercury, and we hit it with voltage and you see how it glows. This one is filled with neon. So you'll be taking the light from these discharge tubes and observing it with a spectroscope. If you're not familiar with spectroscopes, these are instruments that take light and they break the light down into its component parts, its component wavelengths. If you take white light through this scope, the white light enters here. You don't look at the white light entering here, you look at the scale on the side. You'll see that white light broken into a rainbow of colors. You're seeing all the colors of the rainbow displayed here because white light is what you get if you take all the colors of the rainbow and smash them together. It appears to your eye to be white. So that's basically what we're doing today. Now, a little background. You're dealing with electromagnetic radiation here. The light that you're viewing is a form of electromagnetic radiation. You should be familiar with EM radiation from your lectures. If you're not, quick review. Electromagnetic radiation is energy. It's energy that's traveling through the universe at the speed of light. So what you know and love as light, that's electromagnetic radiation. It's a fairly broad spectrum, the electromagnetic spectrum. You're intimately familiar with one small sliver of that electromagnetic spectrum. That's the visible region of the electromagnetic spectrum. That ranges from about 400 nanometers in wavelength to 750 nanometers. If you're not familiar with wavelength, we think of this electromagnetic radiation as energy traveling through the universe as a wave. Just as a wave in the ocean transfers energy, waves of electromagnetic radiation transfer energy. When you're talking about waves, you always talk about them in terms of wavelength. If this is the electromagnetic radiation, the distance between two peaks here, that distance is the wavelength. We give it this symbol, lambda, that weird looking Greek L is pronounced lambda, and that stands for wavelength, the distance between two peaks. So if your distance between two peaks is around here 700 nanometers, that electromagnetic radiation is going to appear to your eyeball to be red light. Out here, closer to 400 nanometers, that electromagnetic radiation with the shorter wavelength, when that hits your eyeball, it's going to appear to be blue light. Your eyeball, you might not know this, is nothing but a fancy electromagnetic radiation detector. And it's tuned to detect radiation in this narrow wavelength. Now there are other wavelengths way out here. You go into ultraviolet radiation, eventually you get into gamma radiation. Out here you get into infrared and whatnot. But that's your crash course on EM radiation. Can you pause? Okay, with electromagnetic radiation, we have some equations that go with this, of course. Whenever you're talking about electromagnetic radiation, you can characterize the radiation either by the wavelength or by the frequency. They're interchangeable. We have an equation. It's this one. C equals lambda nu. Lambda, again, is the wavelength. C is the speed of light. 3 times 10 to the 8th meters per second. This little guy, the guy that looks like the weird V, it's actually the lowercase Greek letter N. It's pronounced nu. And it stands for the frequency of the radiation. That's how many complete cycles of the radiation pass a particular point in 1 second. So when you're talking about electromagnetic radiation, a particular type of radiation, you can specify either the wavelength or you can specify the frequency. If you know the frequency, there's only one wavelength that goes with it. C is constant. So C equals lambda nu, one of the key equations you have to be familiar with here. The other equations that we use, another equation you're going to see is this one. Energy equals h nu. Here in this equation, nu is the frequency, as we discussed. This is the same as this guy, frequency. H is Planck's constant. It's a constant 6.626 times 10 to the negative 34th joules seconds. But more importantly, what are we calculating here? E. E is the energy associated with that radiation. Now, what do we mean by E? Well, here's the story there. We can think of this electromagnetic radiation as being energy transmitted as a wave, or we can picture that radiation as energy that's transmitted as little particles of light called photons. Now, obviously, a particle, something flying through the air, is not the same as a wave which is stretched out through space. Light, electromagnetic radiation, is odd in that if you set up an experiment to treat it as a wave, it will behave like a wave. It'll follow this equation. If you think of that radiation as being a stream of little particles, it'll act like a stream of particles. They call it the wave-particle duality. We're not going to get into that because we're not physicists, we're chemists, and we like to keep things simple. So, anyway, the amount of energy carried by one photon, one particle of the light, that's this number right here. That energy term in this equation is telling you how much energy is carried by one individual photon of that light. And that's related to the frequency of the light. Okay, so we have our two equations that you use with electromagnetic radiation. You may notice there's a third equation that just appeared here. This equation shows you the energy change for an electron when it's jumping from different levels or different shells within a hydrogen atom. This is the Rydberg equation. And let me try and tie this all together for you by showing you a little bit of atomic structure. For a hydrogen atom, the picture of the hydrogen atom that we have is you have the nucleus, contains your proton, and then you have an electron. And the electron has to be in certain allowed orbits around that nucleus. It can be in the first orbit, we call that n equals 1, the second orbit, the third orbit, etc. You might recognize these as the primary quantum numbers that you've heard of in lecture. So these are your quantum numbers. So the electron can be at this level, this level, this level. It keeps on going up. The electron can never really be in between. The electron can be in one orbit or another, but it can't really be in between. So one thing you have to realize about these orbits, the higher up the orbit is, the more energy, the more potential energy that electron has. Think of it this way. You go into a building. You're on the first floor of that building. You have a certain amount of potential energy. You take the stairs up to the third floor. You've got more potential energy in your body on the third floor than you did on the first floor. Think of it. You fall out of the first floor window, what happens? Thud. You fall out of a third floor window, what happens? Splat. So the higher up the level in levels that electron goes, the more potential energy that electron is carrying. So in a so-called ground state hydrogen atom, that's a hydrogen atom at its lowest potential energy configuration, the electron lives here in the first level. If we pump energy into it, that's what we're doing when we excite it in these discharge tubes. You pump energy into that thing, the electron can transition, go from here, it can transition up to a higher level, say the third level. Now he's got more potential energy. Now, eventually, the electron here can fall down to the second level. He can fall back down to the first. Let's say the electron transitions down to the second level. Hey, that electron lost some potential energy, didn't it? Well, first law of thermodynamics says you can't destroy energy. All you can ever do is move energy around. So this electron lost some potential energy. Where did that energy go? The potential energy that's lost from this electron shows up as a photon of light. So when that electron makes that transition, that energy is given off as a photon of light. Well, how much energy is that photon carrying? That's where this equation comes in. The energy change for the electron, how much energy is lost by the electron, is given by this equation where Ni here is the initial level of the electron, and F is the final level of the electron. So you plug those numbers in here, run it through this equation. That tells you the energy change for the electron. In the lab manual, we have that equation written with these straight up and down lines which indicate absolute value. The reason we do that is, well, the energy change for the electron is a negative number. The electron lost energy, it's going to be a negative number. You never get a negative number for the photon of light. Light has a positive energy, so if we use absolute value here, we get a positive value for that. Okay guys, let's talk about what you'll be doing in terms of the report sheet that you have to hand in. You won't be filling it in, we filled it in for you. We'll be showing you the spectrum of white light, which should be a continuous spectrum. So on this continuous spectrum, you should see the colors gradually change from red to blue. And then we'll show you what you would see in the individual discharge tubes. So instead of seeing the continuous spectrum, you see sharp lines. The explanation for those sharp lines is this model of the atom. Since the electron can only make certain allowed transitions, say from the third level to the second level, it can put out a photon with a certain amount of energy, and that amount of energy corresponds to the wavelength of red light. It can do another transition maybe from the fifth level to the second level. It spits out a photon with still more energy. That photon corresponds to having the energy associated with blue light. But since it can only do a few transitions, you only see a certain number of lines in the spectrum. Whereas with white light, you see the continuous spectrum. You see an infinite number of wavelengths as light gradually changes from red to orange to yellow, green, blue, indigo, violet. But again, with the line spectra you'll be observing with our discharge tubes, you don't see the continuous spectrum. So, we'll be supplying you with the data, and then only for the hydrogen spectrum, you'll have to do some calculations. For calculations, only for the hydrogen spectrum do we ask you to do this, but you have to complete this report sheet. Now, what it's asking for here is you calculate the energy of the photon when that electron drops from the third level down to the second level. So those would be the values of n that you're putting into the Rydberg equation. Based on that, you can find the energy of the photon. Once you know the energy of the photon, you can find its frequency using energy equals h nu. Once you know the frequency, you can calculate its wavelength using C equals lambda nu. Those three equations that were on the board earlier. Once you know that wavelength in nanometers, you can tell us what color of light you expect to see in that spectrum from the hydrogen tube. And you can then see if indeed that was the color that you observed. Indeed, if that was the color you observed in the hydrogen spectrum. Again, we'll have this part all filled in for you. This will be the data that you would have seen if you had done the experiment. I'll be sending out a little cheat sheet on how to do these calculations in PDF format to y'all. They're not that tough to do. So that's the calculation part. Now, if you want to talk about why are we doing this experiment, let me give you a quick spiel on why chemists have you do this experiment. Chemists like line spectra for two reasons. One, all this theory here is what led to the development of quantum theory. So by observing these line spectra, working out these equations, we developed modern quantum theory, which allows us to have a pretty good idea of where electrons live in an atom. The second reason chemists like line spectra, the more pragmatic reason. You may have noticed when you looked at these discharge tubes, different elements put out different wavelengths of light. Therefore, you can use the wavelengths of light put out by an element when it's excited to identify the element. Each element on the periodic table will give you a slightly different set of lines for line spectra. Based on that, you can identify the element. So the second portion of this experiment has to do with identifying elements by doing flame tests and looking at the colors that you get off of the flames. Got it? Yeah. Okay, so I mentioned that the pragmatic aspect of line spectra has to do with quantitatively identifying different elements. So in the second part of this experiment, actually I believe it's part C of the experiment, you're supposed to observe the colors that you get when you put different elements into a flame. Since they're all putting out different wavelengths of light, they all give distinct colors. What we have lined up here for you, we have little wooden sticks that have been soaking in solutions of, here we have strontium chloride, so this would be strontium chloride. Here we have sodium chloride, lithium chloride, potassium chloride, copper sulfate, calcium chloride, and barium chloride. So, what you're supposed to do is take one of the sticks, say with the strontium chloride, put it into a flame and observe the color. You seen that nice red color that you have there? Try it again with the lights down. There's a characteristic color of strontium when it's excited, which of course will be different than the characteristic color of sodium. Notice how sodium is more of that yellow. And of course we have lithium. Let's see what that looks like. Need to let the flame calm down a bit. Here's the characteristic color of lithium. See that kind of scarlet, almost a scarlet red. We have potassium, which is typically a nice purple, lavender. Here's our potassium. Copper, we have our wooden stick soaking in the copper. Put that in there, and hopefully you're observing a nice green color. This is the part of the experiment where if you're colorblind, you have to make sure that your lab partner is not colorblind. We have the calcium. And again, you don't have to remember these colors. These are going to be written into the report sheet for you. So calcium gives you another red, kind of similar to strontium. Some people can tell the difference between calcium and strontium. Some people have a little trouble distinguishing. They're slightly different shades of orange red. And finally, we have barium, which is rather toxic, so I'm not going to pick this one up with my fingers. And here's the characteristic color of barium, that kind of key lime green. So you see that each element puts out different wavelengths of light. Based on those wavelengths, you can identify the different elements. In today's experiment on the report sheet, you'll have the observed colors of all of these written into your report sheet. Then you'll have the colors observed taken from an unknown. Based on the color of your unknown, you should be able to identify what your unknown is. So complete the report sheet based on that. Now, just so you know, in real life, chemists haven't really been doing flame tests for some time. We have instruments that will take a sample, heat it to extremely high temperatures so it glows. We'll have a spectrophotometer look at the light, detect the lines. We can analyze for every element in the periodic table in about 2 seconds with a good instrument. But it all started with simple flame tests. Quantum theory started with the observation of line spectra and the equations that were used to describe line spectra. So for your lab report, complete the lab report, submit it digitally to your instructor, and that concludes this video demonstration of characterizing elements.